This is the second video for Unit 7, Lesson 2, Introduction to Probability. And in this video, we'll go through and we'll do all of the example problems that are in your notes folder. So the first example problem says calculate the probability of event A, the probability of event B, the probability, actually it doesn't say the probability of event B, but we're going to do it anyway. We're going to do the probability of event A or B, the probability of event A and B, and the probability of the complement of event A. The first thing you need to do when you work these problems is get all your information organized as best you can. Depending on how the information is written down or how much information there is, if it's a lot of individual numbers or individual letters or individual pieces like marbles and jacks and those kind of things, is trying to decide what your sets are. So we're using a number cube, which is just like an ordinary die. Instead of rolling two dice at the same time, we've only got one. So our sample space is just all of the numbers that are on a die. So 1, 2, 3, 4, 5, and 6. That's our sample space. That's what this S represents, our sample space. It's just how many different things could I land on. I could land on any of those numbers when I roll a die. Event A is what if you just roll a prime number? I just want to roll a prime number. So that set is just the prime numbers. And the prime numbers out of this list are 2, 3, and 5. So that set shows me those three numbers. And event B is what's the probability, or what's the event is, what if you roll an even number? Well, the even numbers are 2, 4, and 6. So 2, 4, and 6 are the set for event B. So just to kind of help us with our notation, we're going to do N of S. This just means the number of elements in the sample space. So we're going to count 1, 2, 3, 4, 5, 6 elements in the sample space, and that's a 6, because that's just how many things are in that space. And then N of A is the number of elements in event A. There's 1, 2, 3 things in that set. So N of A is 3. Same for N of B. There's 3 things. There were 3 numbers in that set. So we're just going to write that down, just to give us to help us get ourselves organized and ready to actually do the probability. So probability is going to be written as the probability of the number of elements in the subset, so the number of elements in your event, over the number of elements in your sample space. So to maybe try and write this in a little bit of a shorthand, we're going to say the number of elements in A over the number of elements in the sample space. Or the shorthand would be this: N of A over N of S. Well, we've already done all that work. We know that there are 3 elements in the event A and 6 elements in the sample space. And as a decimal, that's 0.5. And as a percentage, that's 50%. Same thing for event B. Event B is going to be the number of elements in event B over the number of elements in the sample space, which also happens to be 3 over 6, which is also 50%. That's something that you've done before. That shouldn't be new to you. Maybe organizing it by events instead of individual numbers is new, but probability itself isn't new. Where it gets a little new and gets a little tricky for some people is when we start doing the unions and the intersection. So this first problem that we want to look at, this next probability is a union. And you know it's a union because it has a U shape in the middle of it. That's the best way I can tell you to remember that. It also might be written as an OR. And if you'll go back to that first video, you'll remember that a union is everything in event A or everything in event B. So let's start by combining our 2 events and seeing how much stuff we have in them. So we have A or B, and our set is all of these numbers. So they have a 2, they have a 3, they have a 5, and they have a 6. They share a 2, but they share it, so you don't write it down twice. There aren't 2 of them. There's just one 2, It just happens to be at event A and at event B. So we write it down one time, and we see that the number of elements in A or B is 1, 2, 3, 4 elements. So there's 4 elements in that union. I left a number out, didn't I? I left out the 4. Ha. Let's add that 4 in there. So let's put a little caret. There's a 4 in there. So there's actually 5 elements in that union. Helps if you write them all down. And then we're going to do the probability of an A or a B, something from event A or something from event B, is the number of elements in the union over the number of elements in the sample space. Well, we already calculated that there were 5 elements, 2, 3, 4, 5, and 6, in the union. And we've known since the beginning that there are 6 elements in the sample space. So 5 over 6, let's divide that out. 5 divided by 6 is 0.833. And if you're not given directions on where to round to, just always round to the nearest tenths, hundredths, thousandths place. Round to the nearest thousandths place, because then when you multiply by 100 or you move your decimal 2 places, it'll be easier to get an exact percentage. So the probability that you'll get A or B, event A or B, a 2, 3, 4, 5, or 6, is 83.3%. The next probability we want to calculate is the intersection. And the intersection is the and. And if you remember from the first video, it's the things that both of the elements that both of the events have in common. So let's go back up here and let's look at event A and event B. Things that they have in common. They have a 2 in common, and that's it. The only thing, the intersection of event A and event B, is a 2. That's what they share. So if we were going to come down here and we were going to say, hey, the number of elements in A and B is 1, because the intersection of A and B in set notation is just a 2. That's the only thing that they have in common. So when we do this probability, we're going to say the number of elements in A and B over the number of elements in the sample space. And we're going to find that 1 over 6 is our fraction, and 1 divided by 6 is 0.167, which is 16.7%. The last thing we want to be able to do with this same set of data is calculate the complement. There's 2 ways to do this. The first way is to say, okay, the complement is 1 minus the probability of event A. Because 1 represents the whole thing. Just like 100% represents the certainty that it's going to happen, that 1 represents the certainty that it represents everything, the certainty that this event will happen. So if we take that 1 and we subtract the probability of A, remember if we go all the way back up here, we have that the probability of A is 3 over 6. So let's do it as a fraction, because we don't want to do decimals and get weird numbers. So 1 minus 3/6 is 3 over 6, which is the same as 1/2, which is the same as 0.5, which is the same as 50% when we're doing probabilities. Now, the other way to do this, if you hadn't already calculated the probability of event A, would be to go back and look at all of the stuff that's not in event A. So you would still do the probability of the complement of A, only now you're going to do the number of things that are the complement of A over the number of things that are in the sample space. So if we go back up the page and we go, okay, we want to write a set for everything that's not in event A. Well, event A is 2, 3, and 5. So that means 1, 4, and 6 are not in event A. They're the complement of event A. And so we know now that the number of elements in the complement of A is 3 elements. So we can come back down here where we started our probability statement, And we can say the number of elements that are the complement of A are 3. The number of elements in the sample space are 6, which is the same as 0.5 as a decimal, or 50%. The biggest thing you need to focus on is making sure that you read the probability statements correctly and making sure that you have your information organized so that you're not stumbling around trying to figure out what's in each event when you're looking at your final answer. So starting out by organizing all of your information, even though you don't like doing it, is going to be the best way to ensure that you get the right probability answers. So example 2 was about 30 numbered slips of paper in a presentation in your English class. It said the numbers 1 through 30 are written on slips of paper that are placed in a hat. Students draw a slip to determine the order in which they will give an oral report. Event A is being one of the first 10 students to give their report, and event B is picking a multiple of 6. All right, so let's talk about our sample space first. The problem tells us that the numbers 1 through 30 were written on slips of paper. All right, we don't want to make our lives more complicated, so we're not going to write out in set notation all of those numbers. We know from 1 to 30, we know all the numbers in the middle, and we know that the number of elements in the sample space is 30 numbers. But we do want to organize event A and event B. Event A is being one of the first 10 students. Well, that's anywhere from 1 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I am writing this set out because it's a small set. It's only 10 numbers. And here in a minute we're going to want to look at the union and the intersection of event A and event B. And if we can see all of the elements in each event, it makes it a lot easier to determine what they share and what they don't share. So the number of elements in event A are 10 because we numbered 1 to 10. And event B is picking a multiple of 6. So the multiples of 6, 6 times 1 is 6, 6 times 2 is 12, 18, 24, and 30. So those are the multiples of 6. So the number of elements in event B are 1, 2, 3, 4, 5. There are 5 elements in event B. So when we do the probability of event A, we say the number of elements in event A over the number of elements in the sample space. Well, we know that there are 10 elements here. There are 30 elements in the sample space. You can reduce the fraction if you want to. I just go ahead and divide it out like I see it. And that's 0.333, which is 33.3%. The next thing that we're asked to calculate is the probability of the union of A and B. So that's an OR problem. So we're looking for everything that's in event A and everything that's in event B. Now, you can't just add these two things together because there is some overlap. There are some things that they share. So we don't want to just add them together and go, there you go, that's the probability of A or B. So A or B contains 1, 2, 3, 4, 5, 6. They both have a 6, but I only write it down one time. 7, 8, 9, 10. So that gets everything in event A plus the 6 from event B. Now we're going to list everything else left in event B, which is 12, 18, 24, and 30. So the number of elements in A or B is 1, there's 10, 11, 12, 13, 14. There are 14 elements in that union. So when we do the probability of the union of A and B, we say the number of elements in A or B over the number of elements in the sample space. So we take that 14 over 30, and we divide. 14 divided by 30 is 0.467. So as a percentage, it's 46.7%. The next thing we want to calculate is the probability of the intersection. So we want to look for the overlap, the things that they share. So this is an and problem. So the first thing we want to do is we want to find the set of everything that's A and B. So A and B, and that set is going to start, let's see, they don't have anything in common, 1 through 4 or 1 through 5. They both have a 6, so there's a 6 here. And that's it. They both have a 6 in common. That's all they got. So our set for A and B is 6. So the number of elements in A and B is 1. There's just one thing in that set. So we're going to do the number of elements in A and B over the number of elements in the sample space. And that's 1 out of 30. Which as a decimal is 0.033, and as a percentage is 3.3%. So the probability of you being that 6 that gets drawn is pretty slim when we're putting two events together. The last thing we want to calculate is the probability of the complement of A. Well, since we've already done the probability of event A, I'm going to do the shortcut and I'm going to say 1 minus the probability of event A. And the probability of event A was 10 over 30. And if you want to take that 10 over 30 and reduce that fraction, it reduces to 1/3. Those zeros, you can mark them out. So we can say 1 minus 1/3, and 1 minus 1/3 is 2/3. So the probability of the complement of event A is 2 over 3, which as a decimal is 0.667, and as a percentage is 66.7%. All right, the last example we want to look at in calculating probability with intersections and unions uses a two-way frequency table. Now the two-way frequency table I have given you is missing a little bit of information that you're going to want in order to solve these problems quickly. And I gave you these kind of problems because the sample problems on the state test, this is what their tables look like. And so I wanted your tables to look like what they're going to look like on the state test, and I want you to get used to going ahead and finding some of this information on your own. So what I want to do is, I don't know how many people were surveyed. Actually, yes, I do. The example says, a magazine collected surveys from 240 people about the kind of vehicle they preferred. Their responses are in this table. And then we're going to calculate the probability that someone who responded to the survey was a female. And we're going to calculate the probability that someone who responded to the survey was a man and he preferred an SUV. But let's go ahead and add some of these things together. We want to get a total column here. We want to add this row together. 21 plus 39 is 60. So 60 men responded to the survey. And we're going to add 135 and 45. And we're going to see that 180 women responded to the survey. And then we're going to add the two columns. We're going to add the column about the SUV, which is 21 plus 135. So 156 people preferred an SUV, and 39 plus 45 says that 84 people preferred to drive a sports car. And we can check and make sure that we've done our math, because 60 plus 180 equals 240, and 156 plus 84 also equals 240. So we know that we've got the right number because both of our column for our total and our row for our total add up to the same number. So we're going to use these numbers to calculate the probability that someone who responded to our survey was a female. So we need to know the number of elements in the group for a female over the number of elements in the sample space. Well, the number of elements in the sample space is just how many people responded to the survey. There were 240 people who responded to that survey. And then we want to know, well, how many of them were female? Well, we go to the row for female, we go all the way over to the total, and we see that 180 of the respondents were female. And you can reduce this fraction if you want to. It reduces to 3/4, which as a decimal is 0.75, and as a percentage is 75%. So 75% of the people who responded to this survey were female. So then the next probability we want to calculate is, out of the people who responded, how many of them were a man and he preferred to drive an SUV? The question that, as it's written, says, what's the probability of a man preferring to drive an SUV? Well, that means he has to fit both of those categories. The respondent has to fit into the man category, the male category, and he has to fit into the category for SUV. So we need to narrow this down to just the people who fit in this group. Now, when we did that with the other examples, we took all of our elements and we laid them out nice and neat, and we looked for where they overlapped. With a two-way frequency table, it's even easier. You go to the row for male, you go to the column for SUV, and where those two things overlap, right here, where those two things meet, that is the number of elements for male who prefers an SUV. So look for where those two things overlap one another, where they come together in the chart, and that's going to be your intersection. They literally intersect like two streets. They intersect right there at 21. And it's still all over the number of elements in the sample space, which is the 240 people who responded to the survey. That reduces to 7/80, if that makes you happy. And 7 divided by 80 equals 0.0875. And as a percentage, that's 8.75% of the respondents. So the probability that you pick up a survey and it's completed by a man who prefers to drive an SUV is 8.75%.